All right, so I think I figured something out. And the thing that I figured out can potentially, at the risk of being cliche, it kind of changes everything. And what I've kind of realized is whatever you can imagine as the next great state of cutting edge, kind of whatever, uh, ultimately it's all boiling down to the same thing. And no one is actually working on that one common thing that spreads across all these different domains and industries. What is that common thing? Well, if you work in neuroscience or you work in material science or you work in AI, at some point, no matter, where you start in those worlds and domains, you eventually are going to reach the substrate. You're going to get blocked on the substrate. You're going to want to do things that you can't really do because you don't understand the substrate. When I say the substrate, you could think of it as quantum, but I'm thinking of it more as this is the base layer of reality or the base sort of manifold from which quantum mechanics and the classical world sort of emerges. And what I've kind of discovered as one of the biggest forgotten secrets for technology and people who want to invent and do new things, the biggest area is the substrate, and specifically how consciousness interacts with the substrate. And so, our first investigation, and what this channel will be, is an investigation into the substrate. And I have a feeling that we've been led astray by mainstream neuroscience and physicists. And I know that's a big claim, but we'll explore everything with the full amount of rigor and logic that we can possibly conjure up. And this will be part of a series investigating the substrate. Our first investigation is going to be into consciousness. So buckle up and away we go. But before we get into our first investigation into consciousness, there was one thing that I kind of wanted to set the table with before we launch off, and that is just kind of a frame of mind that I've adopted when looking into this that I think is going to help all of us, at least I hope. And that is, I was thinking about, the great thinkers of the past, your Isaac Newtons, your Werner von Braun's, your Nikola Teslas, and all of these people. And what I noticed is that the great thinkers and scientists and inventors of the past are distinctly different from the great thinkers of today. The main difference is they weren't afraid to try impossible sorts of things. They didn't know what the category of things that were impossible actually were. When Isaac Newton was describing planetary motion, he needed math that just straight up didn't exist, so he invented it. Werner von Braun, he was building rockets, in his backyard as a kid, way before anyone thought space travel was something that was feasible. Tesla had these grand ideas for, electromagnetic sort of fields that anyone could tap into, and he got stuff to actually work. I think he also reportedly believed that the brain was some sort of an antenna or filter slash receiver for consciousness. I don't know, probably nothing. Don't worry about that. But anyway, I was thinking about these great thinkers, and that one thing they had in common was they weren't afraid to try brand new things. Flight, for example, the Wright brothers. If you tried to work out flight on paper in, your office, and I'm going to invent flight and come up with the physics, you would have never done it because flight is one of those things that just isn't fully proven. At some point, you're going to have to deal with fluid dynamics, and when you're dealing with fluid dynamics, you're talking about Navier-Stokes equations. And Navier-Stokes equations are unsolved. They're one of the Millennium Prize problems. They'll give you $1 million if you can solve this. So, at some level, the invention leads the theory. The technology leads the math. We didn't create thermodynamic mathematical models and then create the steam engine. We created the steam engine and then we needed math to describe what was going on, and that's where thermodynamics kind of comes from. So they weren't afraid to try these impossible things, and I would like to adopt the same sort of mindset when we investigate the substrate. Where something can be testable, I would like to test it. Where we can experiment with something, why don't we try and run the experiment or some sort of pared down version? So, with that in mind, kind of where it all starts is with consciousness. So I will try and keep the video at a high enough level that it's understandable if you don't have much background. There is a mechanism that I would like to describe, and that mechanism builds upon the work of others, and then there's one small part that I think was missing that I've tried to fill in and add myself. So when I get to that part, it's going to be a little bit more technical. But anyway, strap in, here we go for real this time. So my first investigation is into consciousness. I recently became interested in the subject of consciousness through AI. So I was trying to build an agent that could beat Pokemon Blue. But I want to be clear here, the goal wasn't to beat Pokemon Blue with an agent. The goal was to create an agent that was capable enough to beat Pokemon, which is a small but important difference. I wanted to create an architecture that would allow an agent to encounter the data in the world of Pokemon, update its goals, set out to beat the game. It would learn how to play like a human would, creating strategies, enacting them, adjusting them over time. It was a grand plan, man. And my approach was to use an ensemble model, which sort of included both a System 1 and a System 2 style of operation. For those unfamiliar, that's from Daniel Kahneman, your favorite behavioral economist, or however you want to describe him, in the field of cognitive psychology. The idea that we have a reflexive, automatic style of thinking, which is thinking fast, or System 1, and a slow, deliberate style of thinking, which is System 2. My plan was to replicate this with what's called a recurrent frame-based action model. Paired with an LLM as a brain. So that would give me my System 1 and System 2. And I also tried to implement this symbolic memory system alongside the frame-based action model called an FBAM. So that would give me an SR FBAM plus LLM architecture. And the reason I went for this was I wanted some fast loop handling the moment-to-moment control, and a slow reasoner, or the LLM, handling the strategy, and some sort of shared memory sitting between them. And also, when the FBAM paper came out, everyone on Twitter lost their minds and said, this is going to change everything, and this is so cool. So I thought maybe I would try and do something with it. So anyway, on paper, I thought this all sounded reasonable. But it fell apart. And the reason it fell apart was because there's no clean handoff. So there's no observer deciding when to switch from System 1 to System 2. In practice, System 1 just kept acting. The LLM requests were asynchronous, they'd fire off, take seconds to come back, and by the time they returned, the game state had moved on. Directives arrived stale, they got dropped, the agent looped on the same screen for thousands of steps, waiting for guidance that either just never arrived or arrives too late to matter. And you can see here on this run, we're perfectly happy to just play the SNES, the SNES. Nothing else happens. Maybe if we play it one more time, though. Okay, one more time. This time, something... No, okay. It might be possible to conceive of a different ensemble model that could work, that could generalize to not only Pokemon but other systems, but so far I think there is enough data from my attempts and from everyone else's attempts to say that agency or free will doesn't come for free. LLMs now are enormously powerful, trained on the entire corpus of human data, and yet free will, you don't get it for free. It doesn't emerge no matter the number of parameters you have training the model. Another way to think about this is all models kind of exist in two states. You have training and you have inference. And when it's in training, the weights are being adjusted, it's making new connections, it's learning. When it's deployed in inference mode, however, the weights are locked. It can't update its own weights. You can have it update some middleware, but the base model weights are locked. And the weights are the thing that's going to determine the probability of its response. It's kind of, a big deal within the model. If you don't have much background, the weights are important. There exists no system which can update its own base model weights while it's in inference mode. You have to retrain at least some part of it whenever you want to update the model, and RAG is a different story. So if this is so hard for AI, that sort of begs the question. And that is, what is it that humans and animals are doing? Humans especially, but it seems as if at least some animals have some element of will or consciousness. You know, dogs have different personalities and behaviors, even within the same breed, but humans are especially unique because we seem to have the ability to rewrite our own loss function in AI terms. We can change what we're optimizing for, even an abstract concept. So someone who becomes a priest is ending their genetic reproduction prospects. They sacrifice that for an ideal. What accounts for this? Why does no other animal do this? And at first, I was optimistic because it seemed like all the great and smart thinkers and neuroscientists had said that the brain is purely deterministic. It operates purely classically, and since computers also operate purely classically, I thought this was very good news for my Pokemon agent. But then I investigated what exactly was going on, and I used this brain map for reference. So you can see this is a diagram of how the brain works, what parts are connected to what, and I have this hanging on my wall, and I extensively studied everything on here, cross-referenced it with whatever data I could find, and what I was looking for was the observer, or free will, or the sense of self, or the thing that would switch between System 1 and System 2 thinking. And after I looked over every part of this map, I realized it wasn't here. It wasn't anywhere. This is why mainstream neuroscientists say that free will doesn't exist. I get it. It's not on this map. But, you know, intuitively that doesn't really seem right because I have the experience of living myself and of consciousness and of making decisions. You know, René Descartes' famous, "I think, therefore I am. Cogito, ergo sum." You know, it's the original bedrock of first. I built this and replicated this architecture exactly. Do I get a thing that can beat Pokemon Blue? Because what I see is the thalamo-cortical loop, and, you know, so thinking about this at some high level, some environmental stimulus comes in, the thalamus ingests that, routes the signal to the relevant area, that area does some processing, maybe somewhere in the cortical area or wherever, that area does some processing, sends the signal back to the thalamus, and then the basal ganglia is either activated or not, which ladders down to the rest of the limbic system controlling the movement. So what's deciding exactly? The brain's chemicals are affecting which neurons are excited or suppressed, but how do chemical reactions give me the aboutness? And why is there a feeling of unity within the brain? Why isn't it all disjointed? And I guess it kind of makes sense to talk about what is it that we're actually trying to nail down? What are the things that we're trying to explain? What are the conscious elements that we want to describe? And Andreas Gómez Emilsson from the Qualia Research Institute, who I'm a big fan of, outlined 4 different areas that we should think to account for. So, the 4 problems. 4 of them. Any real theory has to address all 4. First, why does consciousness exist at all? So this is what philosopher David Chalmers called the hard problem. You could imagine a universe where brains process information, route signals, trigger motor responses, and there's just nobody home. There's no inner experience, there's just processing in the dark. The Searles Chinese room experiment, I'm sure you've heard about that. So why is there something it's like to be you? The classical brain map doesn't really have an answer. It just shows information flow. But information flow kind of doesn't require experience or a conscious observer. The second thing is qualia. So when you see the color blue, your brain is processing electromagnetic radiation around 450 nanometers. But that's not what you experience. You experience blueness, a quality that has no physical description. You can't explain what blue looks like to someone who's never seen it. No amount of wavelength data communicates the experience. Where does that quality come from? If consciousness is just neurons firing, why does anything feel like anything? Why isn't it all just signal processing with no inner texture? And third, the causal properties of consciousness. So if consciousness is just an epiphenomenon, like this side effect riding on top of deterministic physics, then it shouldn't be able to cause anything. but it clearly does. I mean, I decide to raise my arm, and my arm goes up, and it stays there. A thought, a subjective experience, moved physical matter, but how? In a purely classical brain, there's no room for subjective experience to reach down and push the atoms around. You would be violating uh, laws of physics, keeping it high level. But everything is already determined by the prior physical state. That's the important thing. So either consciousness is causally inert, which contradicts our direct experience, or it's entering the causal chain somewhere the classical model doesn't account for. And fourth is the binding problem. So right now you're having one unified experience, at least I hope so. You see colors, hear sounds, feel your body, you think thoughts, and it's all bound together in a single coherent moment. But your brain is billions of separate neurons firing independently. There's no place in the brain where it all comes together. There's no master magic neuron, no central theater. So why does experience feel unified rather than like a billion disconnected fragments? What's binding it? Any theory of consciousness, in my opinion, that doesn't address all four of these isn't a complete theory. So keep these in mind because I'm going to come back to each one. And before we get into the mechanism, I also want to talk about the edge cases, because there's strangeness that also has to be considered. We have to think about the edge cases and what system more or less predicts the anomalies in the data. If we had a bunch of data scattered all around, what theory can explain the variance and sort of the meaty middle of the curve as well as the tails? Outer body experiences are one, or near death experiences, where brain activity has gone to practically zero, yet people report a heightened sense of experience. It feels more real than real. That's the phrase that keeps popping up, according to the people that this happens to. So, less brain activity equals more experience? It doesn't make sense under a classical model. Same for hallucinogens. In the cases of DMT or shrooms or something, the default mode network gets turned down, allowing access to more raw signals of the brain. But when I turn the default mode network down, I still get structured experiences that, again, according to experiencers, I've never done it, feel more real than real. So where is that in the brain map? How would I have predicted that possibility from this classical model? How would I have derived that? When a chaotic and critical system is managing all these complex signals and binding them together, what is the thing which makes decisions that sort of violate entropy and violate biological drives? How does the decision get made? What does that actually look like? And what I began to suspect was that my brain map might be at too high a level. It might not be here. This is like a 30,000-foot view. We need to go deeper to the neurons and figure out what was going on. Where is the selector? What causes the neurons to fire? Or let's say the GABA or serotonin or the dopamine to target specific sites. What is the thing that's actually making the decisions that are going to flow downstream macroscopically to the rest of the body? All right, we're going to get a little bit more technical now and talk about the mechanism a little bit. So I found research showing that neuronal spiking patterns are most relevant for decision making. And that is pretty directly relevant to what is it that's making these neurons fire? What's going on at that level? And this is where the entire thing kind of blows open for me. And that is, I came upon the research of Roger Penrose and Stuart Hameroff talking about microtubules. Microtubules are structures inside of neurons, and they could be the thing responsible for biasing the neuron to fire or not. That might be the thing that I'm looking for. So here's the story. Roger Penrose, you know Roger Penrose, Nobel laureate, one of the great mathematical physicists, etc., etc. He was thinking about Gödel's incompleteness theorem, as one does, which says that there are true statements that you simply can't prove within a formal mathematical system, but humans can still reason about them. So it led him to believe that there was something more than just classical computation going on in the brain. For instance, if I say, this statement is false, if it is indeed false, then the statement is true. and therefore it's not false. So anyway, there's no good way for a computer to resolve this. It's a self-referential paradox, yet here I am, as a human, making a humble video talking about and understanding it. So essentially, Penrose does the math and put out a help wanted ad saying, I found something that could handle these sorts of problems quantum mechanically. Does anyone know of a structure that looks like this in the brain? Enters Stuart Hameroff. He's a professor of anesthesiology at the University of Arizona, and he replied saying that he'd been studying exactly this structure called microtubules. And here's where it gets even more interesting because there's multiple lines of experimental evidence pointing at microtubules. So let's look at some of the data. The xenon isotope experiments. So the way anesthesia works is, well, no one fully knows. But general anesthetics bind to neurons and seem to shut off or inhibit consciousness. That much we can say. And in 2018, some researchers published a study in Anesthesiology, which is the journal, testing xenon with different nuclear spin states. Xenon is a general anesthetic. There's a whole bunch of different anesthetics. Xenon is one of them. So they tested it with this fake xenon, which was chemically identical to the real xenon. So same element, same chemistry, but it has a different nuclear spin. And the nuclear spin shouldn't be relevant at all to classical chemistry. So it's binding to the same neurons, doing the same thing chemically, yet the isotopes with different nuclear spin were around, 20% less effective at shutting down consciousness because they used a mix, some real xenon, some fake xenon. They gave it to the patients or to the rats or to the subjects, and it was less effective at shutting down consciousness, which suggests that something quantum is going on because nuclear spin is purely a quantum property. It shouldn't affect consciousness at all classically. Another piece of evidence or data is the microtubule stabilizer experiments. So more recently, some researchers at Wellesley College or University published a 2024 study in eNeuro showing that when you give subjects a microtubule stabilizing drug before anesthesia, that it delays unconsciousness. So if anesthesia worked purely at the level of the receptor chemistry, stabilizing microtubules shouldn't really matter, but it does. This is direct evidence that microtubules are involved in the mechanism of consciousness. So now that's two independent experimental lines, both pointing at the same structure. How about one more? Bandyopadhyay's resonance work. The work of Anirban Bandyopadhyay at the National Institute for Material Science in Japan. I hope I said it right. Definitely didn't. So his group has been directly measuring the electromagnetic resonance properties of individual microtubules, and what they found is extraordinary because microtubules have fractal resonance patterns. This will matter a lot later, trust me. And they function as time crystals that can generate their own timing architecture. And a single microtubule can store roughly 500 distinct states. 500. I'll get into the details of this later, but it turns out to be one of the three critical ingredients that kind of makes this whole model work. For now, just note, microtubules aren't just passive scaffolding, which is kind of how they're normally thought of. They're active resonance systems. So that's three independent experimental lines, the xenon isotopes, microtubule stabilizers, and now fractal resonance and memory, all pointing at the same structure. The amplification problem. So this is kind of where my thing comes in. The standard objection to quantum effects in the brain is quantum effects are too small. The brain is too warm, too wet, too noisy. Decoherence would destroy any quantum state instantly. And that is a reasonable objection. And it would be fatal if we needed quantum coherence across the entire brain. But we don't. And this is where my part comes in. I'm very excited to share it with you. But the key insight here is that the brain is not an ordinary physical system. Now we're going to get a little bit more technical. So the brain operates at what physicists call criticality, or the edge of chaos. This part actually isn't me. This is empirically established. Beggs and Plenz are the researchers here. They showed in 2003 neural avalanches follow power law distributions, which is a signature of critical systems. So multiple research groups have confirmed this since the brain actively maintains itself at this critical point. So what is criticality? Let me explain. It's an important concept to get, but you probably already understand it intuitively, my dear viewer. But you think about a pile of sand, a sand pile. If you drop grains of sand, one at a time onto a flat surface, at first nothing interesting happens. Each grain just sits where it lands. The pile is called subcritical. It's too stable. Those small inputs produce small effects. Now imagine a sand pile that's steep, supercritical. Drop one grain and the whole thing is just collapsing. The small inputs produce the catastrophically large effects. It's uncontrolled. You drop it and then everything just sort of collapses immediately. It's uncontrolled. But there's this sweet spot in between called the critical point, where the pile is exactly steep enough that a single grain of sand could trigger an avalanche of any size. And sometimes it triggers a small one, sometimes it triggers this massive cascading collapse, but the distribution of avalanche sizes follows a power law. That's criticality. The brain operates right at this critical point, and critical systems have a very special property, which is maximum sensitivity to small perturbations with long-range correlations between components, meaning a tiny input at the right place can propagate across the entire network. And this is what makes the quantum effects are too small argument fail. In a non-critical system, yes, a quantum fluctuation in a single microtubule would be drowned out by thermal noise. It'd be like whispering in a hurricane or something. But in a critical system, that whisper can trigger an avalanche. So the mechanism I'm proposing step by step. All right, step one, quantum superposition in tubulin. So, all right, let me slow down here because this is now going to get, we're getting to the critical threshold of technicality here. So off we go. Proteins are made of amino acids, right? Some amino acids have a special structure, which is a ring of carbon atoms where the electrons aren't locked to any single atom. Instead, the electrons are delocalized, like smeared across the whole ring, like a cloud, and these are called aromatic rings. And they're the same kind of structure you find in benzene. Quantum effects like superposition are easier to sustain in these delocalized electron clouds because the electrons aren't pinned to one location. And each tubulin protein, and remember, microtubules are built from thousands of these. Each tubulin protein contains 86 of these aromatic rings. So tryptophan, tyrosine, one other one I forget. They cluster together inside tubulin in what are called hydrophobic pockets, or regions that repel water. And that helps shield them from the noisy thermal environment of the cell. These pockets are quantum-friendly zones inside an otherwise warm, wet biological system. And what Penrose and Hameroff propose is that the electron clouds in these aromatic rings form kind of collective oscillations. So they slosh back and forth together as dipoles, like tiny synchronized antennas. And critically, these dipoles can exist in quantum superposition, meaning they oscillate in multiple directions simultaneously until a collapse event forces them to pick one. So the actual physical separation in the superposition is extraordinarily small. It's at the level of atomic nuclei on the order of femtometers, so that's like 10 to the negative 15 meters. So unimaginably tiny. But why it matters is the gravitational self-energy of that superposition. That triggers the Penrose collapse. So it accumulates across every tubulin tubulin that's participating. So one tubulin contributes almost nothing, but 10 billion tubulins in superposition together would add up, and it adds up to exactly the right thresholds that trigger collapse at the neural timescales. So one more detail that kind of ties this all together, these hydrophobic pockets where the quantum action is happening, they're the exact same sites where the anesthetic gases bind. So when you go under general anesthesia, the gas molecules wedge into these pockets and then disrupt the quantum dipole oscillations. That's why the xenon isotope experiments are so compelling, because it's the same chemistry, a different nuclear spin, different effect on consciousness. So the quantum properties of the anesthetic are interacting with the quantum properties of these pockets. Did I lose you? All right, so sorry, one more digression. Before I walk through the rest of the mechanism, I want to zoom out just one more time and call something out. And that is, as I researched all of this, the experiments, the theory, the simulations, I kept noticing that there's 3 ingredients that keep appearing over and over again. So every time the model works, all 3 are present. And every time someone objects, they're usually ignoring one of these things. So I want to name them explicitly because this framework is kind of what makes the whole thing tie together. And so 3 ingredients. Ingredient number 1, a critical system. So we've already talked about this, but the brain operates at criticality, the edge of chaos, where small perturbations have maximum leverage, right? Power law neural avalanches, maximum sensitivity, this stuff is well established empirically. Without criticality, quantum effects at the microtubule scale would just be irrelevant. They'd be drowned out. With criticality, they get amplified. This is kind of like a megaphone. It's the critical system. Ingredient number 2, the resonant frequency. So this is Bandyopadhyay's work. Microtubules aren't just static structural tubes, but they're resonant systems. So they vibrate at specific frequencies across an enormous range, kilohertz, megahertz, gigahertz, all the way up to terahertz. And these resonant bands have that fractal self-similar structure we all love, you know, the triplet of triplets. And that's preserved from the scale of a single tubulin all the way up to an entire neuron. So these aren't, you know, like random vibrations. They're like structured, nested, self-correcting time crystals that spontaneously regenerate their oscillation patterns. Why does resonance matter, you may ask? But because resonance is how you get selective coupling. So 2 tuning forks at the same frequency, they transfer energy between each other across a room while ignoring everything else. Microtubules across different neurons, you know, sharing the same fractal resonance architecture, have a natural channel for synchronizing, for talking to each other without needing a direct synaptic wire. So this is how local quantum events could coordinate across neural ensembles to produce that kind of unified conscious moment. Resonance is the shared communication channel. I'm not going to go into it in this video, but there's also kind of another framework, the Saint framework, that we'll talk about in future videos that goes more in depth about these, how these frequencies kind of work. But ingredient 3, it's got to be shielding. So this is the one that kind of addresses the warm, wet, noisy objection head on. And that is that the brain is just too warm, too wet, too noisy, etc. for these sorts of quantum processes to happen. But in an open system at body temperature, quantum decoherence should destroy any quantum state almost instantly, right? So this is, when you ask ChatGPT, it will tell you about Max Tegmark's famous 2000 criticism. He calculated that microtubules could maintain quantum coherence for only about 10 to the negative 13 seconds. So game over, right? But Tegmark modeled the wrong thing. He used a superposition separation of 24 nanometers, where the actual orch-or model operates at femtometer separations, which is like 7 orders of magnitude smaller. And when Hagen, Hameroff, and Tuzinski recalculated them, but with the correct parameters, decoherence times jumped by many orders of magnitude. But even that is still not enough on its own, and that's where the shielding comes in. So microtubules, you know, they're not naked tubes floating in the cytoplasm. They have different layers of protection. So first, the hydrophobic pockets themselves, so those aromatic rings I mentioned where the quantum action happens, it's buried inside water-repelling regions of the protein. The protein is coated with this hydrophilic surface, so water, which is one of the main agents of decoherence, is excluded from these zones by the protein's own structure. The tubulin protein is literally a quantum shield built into the architecture. And the second thing that I was mentioning, the ordered water. So Gerald Pollack at the University of Washington, he's demonstrated that water near the hydrophilic surfaces forms what he calls an exclusion zone, or easy water, or more ordered, it's almost liquid crystalline phase that it excludes solutes and particles. So the easy water forms spontaneously. It grows when it's exposed to infrared energy. So like the sun or something, any sort of infrared energy. The inside of the cell is bathed in the infrared, maybe from metabolic heat. And microtubules, with their hydrophilic surfaces, they would naturally develop layers of this ordered water around them. So Hammeroff and his colleagues, they specifically proposed that this ordered water, along with the surrounding actin gel, creates this decoherence-free zone around the microtubule bundles. That extends your coherence times by orders of magnitude. And hold on, don't say goodbye just yet, because up next, it's the Debye layer. The microtubules are surrounded by this layer of counter ions. So these are charged particles that screen thermal fluctuations from the environment. It's another built-in buffer between the quantum interior and the noisy exterior. One more paper worth mentioning, 2025, it's a new one. Mavromatos and his colleagues, they modeled microtubule interiors as these high Q quantum electrodynamic cavities. So essentially, it's treating the hollow tube as a resonant cavity that can sustain quantum states. So their calculations suggest decoherence times in the order of microseconds under physiological conditions, which is, well into the range where quantum effects could meaningfully interact with the neural processes. So you have the protein structure itself shielding the quantum-friendly pockets. You have ordered water or easy water forming a decoherence buffer around the microtubule. You have the Debye layer screening the thermal noise, and you have the geometry of the microtubule acting as a resonant cavity. So layer upon layer of protection. Anyway, so those three ingredients: criticality, so you can amplify a signal; resonance, so you can synchronize it across the brain; and the shielding to protect it long enough for it to matter. So every time I look at a piece of evidence that supports this model, it's at least one of these three ingredients is doing the work. And every time someone dismisses quantum consciousness sorts of theories, they're usually assuming that the brain is an ordinary thermal system with no special properties. So they, ignore all three of these things. So with that being said, we can get into the rest of the mechanism. We're peeking out on technicality and such. Are you still with me? Leave a comment if you've made it this far. It gets good now. So with those three ingredients in mind, let me walk through the remaining steps of the causal chain. So step one, you have your OR collapse, your objective reduction collapse. So when enough tubulins are in superposition, roughly 10 billion of them, which corresponds to about 8 to 800 L5 pyramidal neurons linked together, the gravitational self-energy hits a threshold and the superposition collapses. This takes about 100 to 500 milliseconds. So the timing of that is not coincidental. It matches the gamma rhythms, the neural oscillations associated with conscious processing and decision making. You might have seen YouTube videos that enhance your gamma wave or whatever. That's kind of what we're talking about here. Kind of. Anyway, step three. Collapse determines local electric fields. So when the electron's position resolves, it determines the local electric field around the tubulin. This, of course, affects how the microtubule interacts with the microtubule-associated proteins, which in turn influences the synaptic weights of those specific neurons. So the way to think about this is like a tiny little zipper, and it lets in either a tiny sodium or a calcium ion, and then if the calcium ion gets into the zipper, that depolarizes the neuron, and that's going to cause it to fire, right? So the wave function collapse controls whether the zipper lets the sodium in or not, in a sense. So the quantum collapse biases whether that neuron fires and kind of how strongly it connects to its neighbors. Step 4 is thermodynamic amplification at criticality. So this is my part here. Those neurons aren't isolated. They're hub nodes in a network that's operating at criticality. So, a small quantum bias doesn't stay small, it propagates. And I tested this computationally. I built network simulations using Xtropic's thermal library, so I'm getting true thermodynamic Gibbs sampling if I take their word for their hardware actually working, which I do, I'm sure it's fine. Anyway, these are not Monte Carlo approximations. This is actual thermodynamic sampling. And I created, different small world networks that mimic the brain topology. I found the critical temperature where the network was maximally sensitive, following research on the brain, and then I applied a small bias to just 10% of those nodes, which you could imagine are the hub nodes. That represents the L5 pyramidal neurons where the microtubules would be doing their thing. So I calibrated these simulations against real neural data as well, specifically rat hippocampal recordings from HC3, and I extracted the avalanche from the spike data in the same way the original criticality papers did. So counting distinct active neurons in 4 millisecond bins, that's the standard Beg-and-Plens methodology, and real rat neurons show power law avalanche distributions with an exponent of alpha 1.6, which hallmark of criticality. The Monte Carlo cascade model reproduced that, about 1.53 alpha, again, right in the expected range. And the thermal model that we did, the thermal icing model, we did them both. So we did thermal and Monte Carlo, but the thermal icing model shows kind of its own critical scaling at a different exponent, which is expected because it's kind of a different dynamical system. But anyway, both are operating at their respective critical points. And so my first test was kind of just constant bias. So applying a steady quantum-like field to the hub nodes. And the results is that biasing 10% of the hub nodes shifted the mean magnetization of the network by about, 0.6 on a scale of -1 to 1. So, the p-values are in the millionths. The effect size is massive. Cohen's D around 1.8. The network moved dramatically because 10% of its most connective nodes got a nudge. That's thermodynamic amplification at criticality. And not only that, it works bidirectionally. Quantum bias in one direction, so you could call it Q+, that promotes a decision. It pushes the network towards a positive magnetization state, meaning more neurons fire in coordination. Quantum bias in the other direction, Q negative, you could think of it as, that vetoes a decision. It suppresses coordinated firing. Both statistically significant, both are highly distinguishable from each other and from a classical baseline. This gives you something neuroscientists have observed, but they can't explain classically. Not just the free will, but the free won't. So the ability to initiate and inhibit action. Benjamin Libet, his famous experiments, you've heard of them even if you don't know them by that name. They showed that the unconscious brain preparation, it precedes conscious awareness of a decision by about 350 milliseconds, which most people interpreted as evidence against free will. This experiment is the one you've heard about where someone is sitting in like a little cubicle and they have to press a button or not. And they hooked their brain up to a machine and it went wow, wow, and it measured their brain, and essentially it saw that the brain lights up before the person presses the button. So they said, oh, well, the brain is determining whether the button is being pressed or not, and the conscious decision is just this after effect that comes afterwards. Completely wrong interpretation of the Libet experiments. There's a whole second half that they don't really talk about. Libet himself points out that the subjects could still cancel the action in the final 150 milliseconds before the execution. So he called this the conscious veto. So the model that we're talking about explains how Q negative bias at hub nodes propagates through the critical network and suppresses the avalanche before it cascades into a motor input. I also ran a critical control test. I created what I call, this classical mimic condition. So instead of biased quantum collapse at specific hub nodes, I applied the same total amount of random noise, just distributed uniformly across the network. So same energy in, it's just not structured. The quantum bias condition and the classical mimic condition, they were statistically distinguishable. So structured bias at hub nodes, not the same as just random noise. So I also ran a unified test with pulsed bias so that we can model the full sequence of like a brain in nature doing its thing. In the pulsed regime, the average magnetization across the whole time series is smaller. It's hundredths rather than tenths because you're averaging over the quiet coherent phases too. But each individual collapse event still is what's doing the heavy lifting. So the pulsed results were statistically significant. I did 40 different runs per condition. Q plus, Q negative was distinguishable at 10 to the negative 15. Q plus differed from the classical mimic at, 10 to the 6th. And the pulsed biases preserves the network's criticality, which is an important point. Constant bias doesn't, of course. So the way you distinguish these conditions under pulsed bias, it's not through raw magnetization, okay? It's through entropy. Q plus produces higher entropy than the baseline. Q negative produces lower entropy. The system stays critical, but the information content changes. This matters because it means each collapse is a fresh amplification event. The network doesn't need to stay pushed. It just needs to be pushed at the right moment. It needs to amplify that push into a cascade and then reset for the next round. So a series of these pushes, each biased in the same direction by sustained conscious attention, is what produces a decision. Not one collapse, many. Each one is reinforcing the last. All right, so now it's time to put this all together as a single causal chain. Are you ready? So we have the quantum superposition in the tubulin at the femtometer scale separation. That gives you 160 milliseconds or around coherent phase across 8 to 800 L5P neurons. Important point here, 8 to 800 neurons, like every living thing is potentially in bounds with this. Fruit flies have enough neurons to have this sort of dynamic happen. Just something to think about. Anyway, the gravitational self-energy then triggers the OR collapse, and that is where your non-deterministic selection occurs. After that, the electron position determines the local electrical field, and that affects the tubulin map binding. The microtubule state then biases the synaptic weights, so the selective edges in the network are strengthened or weakened. Then the neural avalanche is triggered at criticality. That gives you the hub bias, which gives you that statistically significant global network shift, and that ladders up to the macroscopic behavior or the conscious decision. So that's one way to think about the thermodynamic amplification model. The whole point is that you don't need some magical brain-wide quantum field. You don't need coherence across billions of neurons. What you do need is quantum effects and a relatively small number of the right neurons, or the hubs, operating in a network that's sitting at the critical point. Physics just does the rest. And this, by the way, is why the brain maintains itself at criticality in the first place. It's not a coincidence, and it's not a byproduct. Criticality is the operating point that makes quantum influence on macroscopic behavior possible. So the brain has tuned itself to the exact state where the smallest signals have the largest reach. Whether you think that's evolution, which is designed that over time, or something else, we'll leave it there. But in any case, the brain maintains itself at criticality, and it's doing so for a reason. And that brings us, of course, to the big question. So now that we have the full mechanism from quantum superposition in tubulin through the OR collapse, through the thermodynamic amplification at criticality to the macroscopic behavior, there's still a question sitting underneath all of this that I haven't really addressed, which is what is biasing the collapse? Now, in Penrose's OR, it says that the collapse happens The math gives you this threshold, a time scale, the mechanism, but it doesn't tell you which way the collapse goes. So something is still selecting from the range of quantum possibilities. And, if that selection is random, then we're back to square one. We, already kind of established that randomness is an agency. If OR collapse just rolls the dice every 100 to 500 milliseconds, you don't get this self that decides to become a painter instead of a farmer. You would just get noise. Sophisticated, quantum-flavored noise. Still noise. So whatever is doing the selecting has to produce something that random collapse cannot, which is temporal coherence. Consistent directional bias across many collapse events. It can't just be one lucky roll. You need a pattern or a trajectory or a decision that builds over time. And whatever that something is, it also has to account for the anomalies. So the near-death experiences where consciousness persists through near zero, if not zero, brain activity, hallucinogenic experiences where the reduced brain function produces richer experience. And so what we're really asking is, what is influencing the wave function collapse and producing the structured outcomes rather than the random ones, and also persisting through periods of brain activity being shut down? So let's run through the options, and let's run through them honestly, and there's only really a few candidates. Option 1, materialism. Consciousness is just generated by the neurons. It's computation all the way down, and this handles normal brain function just fine. But it has no answer for the hard problem, which is why is there experience at all? And it really struggles with the anomalies. So why does psilocybin, reduce brain activity while increasing the intensity of experience? Why do dementia patients sometimes they regain full terminal lucidity moments before death? Why does a purely quantum property like nuclear spin affect anesthetic potency? Materialism has to answer all of these with a separate ad hoc story. There's really no unifying principle. The second option that you have is classical dualism. So that is mind and brain are separate substances. This explains the anomalies quite well. If the mind is generated by the brain, then reduced brain activity doesn't necessarily reduce experience. But dualism, unfortunately, has been dead for over 400 years because of the interaction problem. How does a non-physical mind push physical neurons around without violating conservation of energy? There's no mechanism for dualism. So option 3 that you have is maybe a panpsychic model. This one's getting more popular, I see, with neuroscientists and people who are kind of getting to the end of the rabbit hole here, and that is consciousness is this fundamental property of matter, like mass or charge, and it addresses the hard problem elegantly. So, experience doesn't emerge, it's built in, it's more core, more fundamental, but it does still create the combination problem, which is how do billions of micro experiences combine into one unified experience? And it also doesn't really offer any mechanism for the anomalies. So option 4, and the option that I like the best, is, well, the brain doesn't generate consciousness. It's a receiver/filter model with a quantum interface. The brain receives and constrains the consciousness or the information. So the quantum effects provide the interface where consciousness enters the causal chain. Then thermodynamic criticality provides the amplification. You see, the last option does something none of the others can do. It explains the anomalies as first-order predictions instead of a post-hoc accommodation. It gives you less filtering equals more signal. That's why the psilocybin produces more intense experience when it turns down the default mode network. A failing filter releases the signal. So that's why terminal lucidity happens, and it solves the interaction problem that killed dualism, because OR collapse is where mind meets matter. So it's not that the consciousness is pushing around atoms, it's selecting among quantum possibilities that physics already allows. There's no energy violation. You're just selecting a possibility from the Heisenberg space. And if you remember what Tesla reportedly said that I mentioned earlier, the brain is a receiver or an antenna, The intuition is very old for this, and this is where the argument gets uncomfortable for some of you people. But if you look at the scorecard, materialism explains normal function but fails on the anomalies and the hard problem. Dualism explains the data but has no mechanism. Panpsychism handles the hard problem but creates new problems instead. The receiver model with a quantum interface is the only one that explains normal function, the anomalies, the hard problem, while providing a testable physical mechanism. It's not the most comfortable answer. It's the one that with the fewest holes. And there's a specific, well-studied quantum mechanism that explains exactly how this kind of sustained selection would work. The physicist Henry Stopp at the Lawrence Berkeley National Laboratory has been working on this problem for decades. Stopp worked directly with Heisenberg and Pauli. He's not a fringe figure. His key insight is that von Neumann's formulation of quantum mechanics, there's 3 processes, right? Process 1, process 2, process 3. Process 2 is the normal evolution of the quantum state. That's the Schrödinger equation. It's deterministic, no choices. Process 3 is the collapse. That's the answer that nature gives when you ask it a question. That's some way to think about it. Process 1, that's the one that everyone ignores, and that is the choice of what question to ask. Which measurement basis do you project onto? What do you choose to attend to? Standard quantum mechanics has no explanation for process 1. It's just the experimenter chooses. But Stopp's argument is that process 1 is where consciousness enters the picture. You, the observer, the viewer, choose what to attend to, and the specific quantum mechanism that translates that choice into physical influence is the quantum Zeno effect. This provides a mechanism for our intuitive experience of, how we go around the world. So anyway, here's how it works. The quantum Zeno effect, it's a real experimentally verified phenomenon. If you repeatedly observe a quantum system, or more precisely, you repeatedly interact with it in the same measurement basis, because we want to be specific, you prevent it from evolving away from the observed state. So each interaction resets the system's evolution clock. The way to think about it is, I'll put it in the description as a video, but you're like a prison guard. You have a prisoner with a 100% chance of escaping if you leave them alone for 4 hours, but the probability of escape starts at 0% and then gradually climbs towards 100%. So if you check after 1 hour, there's a 25% chance they've escaped. But every time you check and find them still there, the counter resets to 0%. Are you following? So if you check every minute, the prisoner isn't going anywhere. If you leave them alone and don't interact at all, the odds that they'll be gone go up and up and up until eventually you hit 100%. So the more you check, the more likely it is that they're still in jail. If you leave them alone, poof, they're gone, okay? So why this matters for consciousness is random collapse is memoryless, okay? Memoryless, random collapse, doesn't have memory. Each collapse event is independent of the last. There's no accumulation, no direction, no persistence. But QZE, mediated selection, Zeno effect, mediated selection, it's the opposite. It's sustained attention, repeated interaction with a quantum state in the same basis. That produces correlated outcomes over time. The system is held in a preferred subspace, not by force, but by the frequency of interaction. You're not forcing the outcome. You're repeatedly asking the same question. And every time you ask, you make it harder for the system to drift away from the answer you're attending to. So this is the difference between randomness and will. Random collapse gives you a coin flip every 100 milliseconds. QZE gives you something that builds, a sustained bias that accumulates across many collapse cycles into a coherent decision. And there's a flip side that makes this even more interesting, which is the quantum anti-Zeno effect. So if you measure at the wrong frequency, you do it wrong. You do it too slow or mismatched to the system's natural dynamics, you don't freeze the state, you actually accelerate the decay. So you make the system evolve faster away from where it was. So it'd be like taking the prisoner and shoving him through the bars out the window or something. So what it means in the context of the brain, the frequency of conscious interaction matters. The gamma oscillations, the 30 to 90 hertz rhythms associated with the conscious attention and binding, these aren't arbitrary. They might just be at the frequency at which the brain's quantum measurement process operates. Too fast and you freeze the system. So maybe that's the paralysis of like extreme anxiety or something where you can't decide anything. Too slow and you get the anti-Zeno effect. So the system decays, the coherence is lost, the attention dissolves. At the right frequency, which is gamma, you get sustained coherent selection without the freezing. And if you notice something, this maps directly onto what my pulsed bias simulation showed, which is constant bias, which is like measuring at infinite frequency. That pushes the network away from criticality. It freezes it. But a pulsed bias, matching the actual OR collapse timing, that's the 160 millisecond phase followed by the 40 millisecond effect phase. You remember that? That preserves criticality while still producing distinct outcomes. So the simulation independently arrived at the same conclusion that quantum Zeno effect predicts, which is the timing of the interaction matters as much as the interaction itself. Stop published this framework in Mind, Matter, and Quantum Mechanics in 1993, and he's been working on it since. There's something in Mindful Universe, and there's something in there, and then there's papers like Quantum Theory and Free Will in 2017. Anyway, what I'm adding to Stop's framework is the thermodynamic amplification piece. So Stop showed that the quantum Zeno effect provides the mechanism for mental causation at the quantum level, and what my simulations show is that the critical network amplifies that quantum level selection into the macroscopic behavior. So Stop gives you the selector, criticality gives you the megaphone. So let's go back to those 4 problems and now resolve them all. So number 1, the hard problem, which is why consciousness exists at all. Well, in this model, this filter-receiver model, consciousness isn't generated by the brain, it's fundamental. The brain isn't creating experience any more than a radio is creating music. The radio receives and filters and then transduces a signal into sound, just like the brain receives, filters, and transduces consciousness into an embodied experience. The reason there is something it's like to be you is because you, the conscious observer, you, dear viewer, exist independently of your physical hardware. The brain is the interface. It's not the source. You are more than just your body. The next one, qualia, the blueness of blue. Remember that one. If consciousness is non-local and the brain is a receiver, then qualia are properties of the signal, not properties of the neurons. The neurons process 450 nanometers of electromagnetic radiation, giving that signal to the kind of bottom layer of the dendrical architecture. The dendrical neurons, I forget the words. You, the non-local observer interfacing through the quantum collapse, you experience blueness. The qualitative character of experience comes from the consciousness side of the interface, not the physics side. This is why no amount of neuroscience will ever explain what blue looks like, and that's because you're looking at the wrong side of the equation. Finally, the third one, which is the causal properties, which is how thoughts move matter. This is where the thermodynamic amplification model directly answers the question, which is consciousness enters the causal chain at the quantum level through the OR collapse in microtubules. And it's not just this epiphenomenon riding on top of the deterministic physics. It's selecting from a range of quantum possibilities. That selection, dear viewer, propagates through the thermodynamic criticality into the macroscopic neural avalanches and ultimately into behavior. So a thought moves your arm because the conscious selection biases the quantum collapse. That biases the hub neurons, which triggers a cascade through the critical network, which activates the motor pathway. That's a complete causal chain from the subjective decision to the physical movement, and the link is quantum mechanics amplified by criticality. Let's move on to the binding problem, which is why the experience is unified. So the OR collapse, of course, provides a natural binding mechanism. So remember, the collapse happens across the ensemble of 10 billion tubulins, spanning, maybe 8 to 800 neurons, but it's a single quantum event. It's resolving across multiple neurons simultaneously. So that could be your binding. It's not that the separate neural signals are getting stitched together somewhere. It's, the quantum collapse is inherently a unified event happening across the ensemble. In Bandyopadhyay's fractal resonance work, that provides the physical substrate for how this coordination happens. If the microtubules across distant neurons share the same self-similar resonance architecture, the same triplet of triplet frequency pattern, they have a natural channel for synchronizing. They're just literally tuned to the same frequencies across millionfold range of scales, and the time crystal structure means that these oscillations are self-correcting and persistent. You don't need a wire even connecting them. The resonance itself is the connection. So one collapse, one moment of experience binding together whatever information those neurons are processing. The timing of the OR collapse, 100, 500 milliseconds, it also matches the temporal resolution of conscious experience. You don't experience individual milliseconds. You experience moments. Those moments are the collapses. They're happening right meow. All four problems, one model, and the thermodynamic amplification mechanism explains how it scales from quantum to macroscopic. And the edge cases, remember the edge cases? Those resolve too. Near-death experiences make sense. If the brain isn't generating consciousness, but it's instead receiving it, then when the receiver is damaged or shutting down, the signal doesn't just stop. It's now just unfiltered instead. So less brain activity, more raw experience, more real than real. The hallucinogenic experiences make sense. So if the substances like DMT are disrupting the brain's filtering mechanisms, the default mode network, you're not hallucinating, you're perceiving more, not less, with the filter dialed down. And free will all of a sudden makes sense. It's not an illusion created by deterministic neurons. It's a genuine quantum level selection process, amplified through thermodynamic criticality into macroscopic decisions. Boom. As far as what would falsify it, if someone demonstrated that microtubule targeting drugs had zero effect on consciousness or its timing, that would be a serious problem. So far, we have the opposite of that. If OR collapse is experimentally ruled out somehow, someone conclusively shows that gravity plays no role in the wave function collapse, that specific mechanism would fall apart. Personally, I'm not too tied to the gravitational self-energy idea necessarily. I think it could be what happens absent some sort of conscious observer, maybe in like some weather system at criticality. They would provide the deterministic kind of collapse sort of events where consciousness might bias it differently. But in any case, that might, be trouble for that mechanism. If that falls apart, someone finds, some experimentally ruled out way that the wave function collapse happens, or someone says that the wave function doesn't even exist, sort of thing. I've heard that before. So that doesn't make sense to me, by the way, that the wave function collapse doesn't exist. What else? If someone found, a unified materialist explanation for the anomalies, some single mechanism that explains psychedelics, terminal lucidity, near-death experiences, isotope sensitivity, all of that without special pleading, then that would cause me to update. And if someone, built an AI that spontaneously developed genuine goal revision without it being hard-coded in, that would mean agency can emerge from computation after all. And, my whole starting premise kind of weakens, but I don't think any of those are likely, but did want to call it out just for completeness. These are the sorts of things that you might expect to prove me wrong. Wrapping up, this leaves us with a very interesting next step, because we can surmise that consciousness is non-local, that it originates from somewhere else, and we can directly affect it with different chemicals. So in other words, we can tune down the filter at times. We can potentially communicate in a bidirectional manner with what exactly? What is the nature of this conscious realm? That will be a discussion for next time, but as a teaser, the answer has been right in front of this entire time. And when I realized it, I felt stupid just So stupid for not having realized it earlier. It's so simple. But if people were serious about actually building breakthrough tech, you know, actually changing the world, this is the next things that I talk about is going to be the things that they would be working on. That's what I think. And that's partly why I'm working on it. So I'll share more next time. Make sure to like, comment, and subscribe. It's been a pleasure. Thank you. And all the simulations, code, data is a full investigation. It's linked in the description. Run them yourself. Check my work. That's the point. The proof is not reliant on me, you know, massaging it. Just go check it out yourself. Anyway, links and stuff in the description. Thank you all for watching. If you made it this far, I'm really especially curious. Leave a comment, say, I don't know, say something like, whatever, just say whatever. All right, I'll see you guys next time.